Welcome back to my YouTube channel. Today I'm talking about the rnorm function in R. The rnorm function generates random values from the normal distribution. The only required argument is n, which is the number of samples you want to generate from the normal distribution. An also argument is the mean. So the default is 0, but you can specify that to be any value you want. And the next optional argument is standard deviation. The default is 1. Obviously, standard deviation can't be negative. Or 0. I think 0 will often throw an error. Okay, so let's get started. No, 0 won't throw an error. It just gives you like all the same value, which would be weird, but not an error. I'll try it later. Okay, so I'm going to do 100 samples from a normal distribution with mean 0 and standard deviation 1, which is a standard normal. That's what we call it. And then I'm going to do the mean of x. And at the shorthand, I'm going to do semicolon, which is essentially saying next line. Treat these as separate statements. We have mean somewhat close to 0 and standard deviation right on that 1. Okay? So if we plot the data, we get the plot of a normal distribution. The tails are plus or minus 3 like we'd expect, because all the data should be around 3 standard deviations plus and minus the mean. Or 99.7% of the data. Okay? But of course we can also specify values for the mean and standard deviation. The mean equal to 5, and before I begin, I'm going to try to specify 0. I think it might, didn't throw an error, although it probably should have, because all it's going to do is print a bunch of 5. Okay, so no error, but not really helpful. Great. Okay. So let's go ahead and see what else we can do with these normal values. Primarily, you may want to get intervals. I want to make a new x vector with a lot more data, so I can get nice quantity. One thing I like to do with sampling is get probabilities or quantiles in the distribution without using the p norm and q norm. I find it to be more intuitive and a good way to take your answer. Okay, so I have a counter variable that's going to count up every time a condition is met. So for I in 1 to length of x, so I'm saying 1 to 1 million here, because that's the length of x, the length of this vector right here. So this I is going to start off at 1 and then go to 1 million. If a conditional statement x of I is less than 1, I actually want less than 1, sorry. And x of I is greater than negative 1. And for this, I don't need to worry about it being inclusive of 1 and negative 1, or the equal to sign, because in a continuous distribution, it never equals exactly 1. the probability of any specific point value is 0, so I don't need to worry about that. So what I'm saying is, count up if it's between 1 and -1, or between 1 and -1 standard deviation, that middle, the plus or minus 1 standard deviation. So we know from about the standard normal that 67 or 68% of the data value should reside within plus or minus 1 standard deviation. And this simulation will show that. So it's just a for loop, this conditional statement, and then a counter that counts when that's true. Okay. So I have my counter divided by the length of x, and we get 0.68. That's exactly what we'd expect. Let's do that again. And now I'm just going to change it a little bit to 2. And of course, we could get, you know what, I want more accuracy here, so it's actually not 2, it's 1.96. And we're going to actually acknowledge that. Okay, so we could get 95% here. And great. This is a great way to approximate values. These are not exact values, we did them by simulation. We get more and more exact answers if we increase n from 1 million to 10 million to 100 million, although we'd essentially run into time and memory constraints. But this is a great way to check your work when you do calculations using p-norm, q-norm, or a lookup table. It's a great way to get answers that don't rely on you getting the right tail. It's much easier to think like, hey, I want values between 1 and -1, rather than I want this side of the table, so I need to cut out this side, so I gotta do 1 minus that if I'm doing p, and it gets confusing, even for more experienced people after they haven't done it for a while, and I tend to prefer this to take my work. Okay. So, switching gears here, we also have the normal distribution to simulate random data. I very often do this. So one of the assumptions of linear regression is normally distributed errors, and we have the normal distribution right here, so it's easy enough to simulate that. So I'm going to do 100 value from standard normal, doesn't really matter here. And I want my y to be 2 times that plus 3. So this is the intercept model. It's to be the coefficient on x to be 2 and the intercept to be 3. But I also have this random noise that should be normally distributed. That's an assumption we make when we use linear regression. Okay. So I now know the mean and standard deviation of my error because I just made it. So what that look like? So summary LM y is distributed as x, and we just quickly, easily mated regression data. So we have the estimated intercept around 3, estimated x around 2, and we have some standard error, which is around 1, which is correct because the standard deviation of the error was around 1. We can confirm though based on about 10,000. We'll make it more robust. I feel like academics use that word too often, but whatever. When it's robust, it's robust. Okay? So we got in stuff even closer to 3. Got the coefficient on x even closer to 2. And our standard error looks a heck of a lot like 1. Okay? So we can generate random values. We can use it to calculate proportions in this histogram, or a potentially better histogram. In this histogram, we can get like the proportion right here, and we don't have to use P and Q norm if we just want an estimate. Although, obviously sometimes you want the exact answer, and it's helpful to compare the estimate to the exact answer using P, Q, or D norm, or a lookup table. And we can simulate data for linear regression, or really all sorts of different regression types. Okay, that's the end of the video. Thank you for watching.